I'm gonna give you a few minutes to settle up, take your time, take your place. The swings are very nice here. Nobody spits, you can sit in the front row. Perfect. Looks like everybody's in. Awesome, let's start. Hello, nice to see you again. Nice to see you coming back and again to ETHWarsaw meetups, even though we keep repeating the same speaker. So open comments. Anybody wants to speak during our meetups, please find me or Monika or Paweł or anyone from ETHWarsaw team. We're open for speakers. And I'm really excited to be here today because if some of you know, I used to work at this office for a very, very long time. And right now, I can give my own interpretation on how I would like the weekly meetings to be held. So right now, we're gonna do a meetup that's gonna be more my style. So this time we're hosted by Ramp. If you've been in crypto for more than like 2-3 years, you know that Ramp has been here for a long time. You don't remember that probably, but the first office for Ramp was the size of like, I don't know, it's like a very, very small bunker. We had no windows, no access to daylight. Right now, plenty access to daylight, very fancy office. A lot of growth has happened. So we're going to talk a little bit about that. And we're going to welcome the speakers from Ramp team to tell us about how they developed over the years, how the product has changed. But we're also going to have a guest speaker from vLayer. So Mark is going to talk about smart contracts a little bit. And after that, we're going to have the usual pizza break, networking. But this time's a change. If you want to do a lightning talk, hit me up. You can do lightning talks. And that's a rule for all of our meetups, that if you want to do lightning talks after the presentations, you're free to do so. And I'm running out of jokes. I've said everything I want. Of course, and it's my grandma calling me. Perfect timing. Sorry, skip it. Let's start with Łukasz. So the first speaker is Łukasz Hanweiler. Yay! Here you go.
Hey everyone, it's great to see you. ETHWarsaw is very close to our hearts because for so many years we are participating in your events. We know, of course, Paulina and Monika and all of the organizers. So it's great to have you in our office. So it's not the first time we see each other. We are super excited to have you because many members of our team also participate in your community activities. And finally, it's also time that we can host you in our Warsaw office. So it's great to have you. We also have some team members from our London office. So Gina, for example. Hey, Gina. We also have Taz somewhere downstairs. Okay, but he'll be back. And today, maybe let's start for those who don't know what Ramp is. So Ramp is a service where you can on-ramp and off-ramp, meaning you can convert your fiat to crypto, and then you can convert back from crypto to fiat. And my first thought when I joined this company like 3 years ago already was that why this is so complex. You only have like widgets, 5 screens, and that's it. But to my surprise, like half of the company basically is not a tech team. It's basically legal compliance and all of the other stuff required to operate on so many markets. And thanks to this, we can offer a global service ranging from Poland, UK, US, LATAM, and other countries. And the whole complexity of the product comes from serving all of these countries with different regulatory setups, with completely different risk appetites. And what I keep repeating to my friends when they ask, hey, why this is so so complex and what's the challenge in this, I'm saying that compared to some other industries which are regulated as well, the challenge, like, the main challenge here is not that it's regulated, but it's being regulated, which means that today it's like this, and like 2 months from now it can be much different. Something what you can right now experience, for example, with what's happening in US, that you could check it every 2 months and you'll be up to date. And right now, if you didn't check it yesterday, maybe you already lost the current direction of what's happening. So this is our these things are our daily lives here at Trump. You can also learn some more stuff how our internals work thanks to Arthur's presentation today. Arthur will also talk a little about the journey, how the system evolved like over time, where we started and where we are today. And we are also happy to have Marek Kirejczyk with us from Vilayer. And Marek is also, I think, one of the key people in Web3 industry here in Warsaw and in Poland. So we are super happy, Marek, to have you. Of course, we are hiring. So if you want to, if you are not, if you didn't panic after hearing about all of the regulatory stuff, these are the open roles which we are right now hiring for. If you have any questions, you can ask Gina here, who's responsible for this. But also there are many team members here, and you can also like ask me if you like to. And I wish you a great evening. Again, super excited to see all of you here at Ramp office. Thank you.
Yeah. Hello, my first trick was teleporting from here to there, so Łukasz couldn't find me with the mic. Yeah. My presentation will be about Ramp's history. Łukasz already told you what Ramp is. I will tell you what Ramp was. And to not bore you with a further introduction, my name is Artur. I work at Ramp since its inception. So I will tell you what we did in the long years past. What even is Ramp? This is an exclusive content, some slides from the OG Ramp pitch deck from 2018. Basically, we discovered that there are lots of crypto products that have lots of users that work well within those products, but they can't move easily between the worlds of traditional finance and crypto finance. Thus, they can't achieve adoption. And the problem is friction on those boundaries. So what do we really try to solve is that we have people with money in bags, like actual money, and people with crypto money that they want to change their money to different money, in simple words. But this is not so easy. You can do it online on crypto exchanges, but this requires complex knowledge both on the technicals of the wallets and also on interfacing with an exchange, because this is a very complex thing for people not in finance usually. You could also exchange crypto for fiat in real life, like local Ethereum, local Bitcoin, etc. But this has its own risks, from getting scammed to getting stabbed. So we want to make this better. But it also is not easy, because putting a trusted party in the middle is not what blockchain is about. It's exactly the opposite. And we don't want to be a policeman that you need to trust to be able to interact with the world. But we can maybe automate it. On the crypto side, it's easy. We can have smart contracts. But on the fiat side, we would need like a magic wizard traffic controller to orchestrate all the events. And the RAMP's original idea was to use open banking. Open banking was like a law initiative by the EU and the UK even before, that banks must have a public API for all licensed parties to get access to user bank accounts by their approval, of course. And we wanted to leverage that to make the exchanges between crypto and fiat completely peer-to-peer. And I will show you in a couple of minutes how. Yeah, so the idea is to put us as the magic wizard traffic controller. So in an overview, this sounds simple. We can create an escrow contract. This is very easy. This is like an one exercise on the first day of the course. A seller wants to sell crypto, buyer wants to buy crypto. They deploy a contract. We confirm the bank transfer, and it's completed. But it has many issues depending on how is it implemented. So either we have to wait between the rounds, the users have to interact with each other, which prolongs the transaction, or if the contract is deployed upfront, then the buyer, maybe they don't have Ethereum to trigger the contract. They want to buy Ethereum after all. And what we did with that was that once the seller has deployed the escrow contract and put their crypto in there for the buyer to get, once we confirm their transfers, the buyer can sign a message, basically, because, as you know, private keys in Ethereum are ECDSA private keys. Yes. So ECDSA signature, so you basically can sign any message with the private key. This is even supported by the wallets, usually in a very weird and ugly way. But then came the EIP, Ethereum Improvement Proposal 720, which introduced a typed interface to have like pretty messages that can have defined properties and can be signed. So basically, in your wallet, you will see, oh, you are signing a message to approve. You are claiming the trade on the RAMP network for this many Ether, for this many fiats, and so on. And when you sign that with your wallet, we know that for sure you're the owner of this wallet and you want to do this. And then we, as RAMP, can initiate the crypto transaction. Basically, we take your signature and we take it to the blockchain. We pay for the gas because you don't yet have any crypto to trigger any methods on the contract. But this still is not ideal because remember in the beginning, the seller had to deploy the escrow contract, and this is expensive. So our next invention was multi-escrow mothership contracts. We named them so internally. So again, with a single contract, the code deployment is paid every time, even though it's always the same code. And it's paid by the seller, so they are not incentivized as much to interact with our system. And we can't store all the data in there because it's also costly. But if we store less data, it's less secure. Like people have to trust that we correctly know the rest of the details of the trade. And also we need a different contract for different assets. This was also another issue which complicated the deployments a bit because tokens are transferred differently than Ether and other assets. So I wanted to put them all in one contract. It sounds simple, but it's not so simple. Basically, then we pay the deployment cost. it's a bit bigger because it's a more complex contract, but it's done only once, and then everyone can interact with it for cents. And then we stored only the hash of the purchase details. So we only store one big number on the chain for every transaction that the users make, which is still secure because we had in our documentation, and there was a description, how can you yourself verify that the details are correct. If you have all the details and all the seller has all the details, then you can do it, verify the hash is correct, and then other people also don't know the details about this transactions. And this way, we could also support different types of assets in the same contract, because we just send a magic data struct that can describe polymorphically any assets types. And I will show it in a couple slides. Basically, we had our Oracle contract. We'll come back to why is it an Oracle in a moment. That initiates and orchestrates the transactions. It can create the transaction. Then the buyer can claim the transaction, but we execute it as the Oracle, and with the buyer's signature in here. Because previously in the create transaction method, it was the ramp Oracle signature, because only this Oracle wallet is allowed to operate on this contract. And then it's the buyer's signature, and then it's the final function to release the funds from the escrow to the buyer, which can also be only triggered by the Oracle or also by the seller in case something doesn't work and they just agree to it. And this is the magic struct I was talking about. So basically, to save storage space and to make it even more efficient, we send the data in a row structure with bytes. So to get the amount of the trade, to know how much crypto to send to the buyer, basically I had to write assembly, extract the amount from the correct byte offset. So it was a nice exercise in low-level programming. And this is also how we managed to save space 2 or 3 times. And this is also how we managed to support different types of assets, because we can support, we have just one argument, which is the struct, and we can support Ether, and we can support tokens. They just have different structure of the info inside, and the structure for the tokens also has more data, like the address of the token. And this product thrived. It was a nice proof of concept. Users could swap, as in ramp swaps. This was our first product, swap crypto to fiat peer-to-peer. But the problem was market fragmentation. Usually there was not enough sellers for the buyers that wanted to get crypto, and also sellers usually wanted to sell more crypto, or there was just a mismatch between the amounts. So we decided to go one step further and separate the buyers from the sellers even more. So the sellers would instead create liquidity pools, like bigger sell offers from which the engine would then sell portions of the crypto to different buyers. And then we thought, why limit ourselves? Why limit ourselves to seller wallets? It can be a contract. And thus, we moved on to the next product, which was already called Ramp Instant, which is we moved to serve more users. It was user-facing. It was meant to be embedded in crypto applications, like now, like the widget you know from now. And the the seller side was hidden from the users because they don't need to know about it. But we had many liquidity providers. Each of them could have a contract with different cryptos they want to sell. And then the multi-escrow mothership contract was authorized to by the seller to take the funds from the liquidity pool contract and conduct all those escrow transactions, all those little escrow transactions exactly as before. So this solves the crypto side. And another benefit is that Ramp can also be a seller in this scheme, which is convenient. Once we get bigger, we can have more volumes and we can easily source more crypto to supply this system. Yeah, and thus the Ramp Instant, our second product, was created. Yeah, so the flow I already described it is that the seller would deploy the liquidity pool contract and then but the seller would now be a contract, not a person. And this allowed us to fix the market making issue. Yes. And now finally to the Oracle part, because I still didn't describe it. How the hell do we confirm bank transfers in a trustless way? So when a seller registers at Ramp, they granted us a PSD2 AISP grant, which is like the PSD2 is that regulation name I mentioned, and AISP is Account Information Service Provider. So basically, this allows us under the approval of the user to end our license to use the bank APIs to get information about the bank accounts on the user from the user. We don't really care about the balances in there. What we want to do is to confirm that the bank transfer between the seller and the buyer did occur correctly. So we get these permissions both from the seller and the buyer. And also to make the whole flow simpler from the buyer, we also can allow them to leverage the other open banking API, which is transfer initialization. It looks similarly to Blick and other quick wire transfer online apps. So basically, you are redirected to your bank with predefined details about the transfer, and we then are sure that the transfer will be delivered exactly where it should be and exactly for the amount it should be. And then we only can watch for the confirmation on the account API. But in this scheme, it's still Ramp that does all the orchestration, and you still need to trust us that we do it correctly. So we are still a trusted party, and I promised you trustless peer-to-peer swaps. So can we do better? Obviously, the issues are that we could fabricate the proof. Even if we have the proof, it still needs to be verified somehow, autonomously. And there are limited capabilities of validation of proofs and signatures on the Solidity language in the EVM machine because of how it's built. Yeah, so the spoiler alert is that it's probably not possible in general because there is no hard link between the digital world and the physical world. But maybe we can move the trust somewhere else where it doesn't matter and where there is no incentive to cheat. So what if I told you there is a computer that cannot cheat? Looks like exactly what we need here. Intel SGX as a trusted execution environment. It's like a cryptographically provable computer. It was largely theoretical for a long time, but then Intel implemented it as an add-on in their CPU hardware, and it's also sometimes called a secure enclave. So whatever code you put into there, the enclave can then present the code is still there, and you can, if you verified the legitimacy of the CPU with Intel's signatures, then you are sure that this computer does exactly what it is presenting to do, because the code and the state of the machine is signed, and that is verifiable against Intel's services. Yes, proof of compute by Intel, yes. And basically, you have a computer that can't cheat, and you can prove it. So how would it work? We as RAMP would be an Oracle operator in this scheme. We would register our Oracle program in the Oracle registry, and then everyone can attest that our Oracle is running exactly the code that we say it is, and that it is valid and correct. And how it would work in our system? Exactly like before, just on the bank transfer confirmation step, there is another magic box happening. Once the transfer is detected, the code in the secure enclave calls the bank API, gets the transfer confirmation, verifies that it's for the correct amount, destination, and so on. It then signs all this data with its own enclave key and submits this directly to the escrow contract on chain. So the only element interacting with the blockchain is the secure enclave, which is provable to be correct, and you don't need to trust anyone else besides Intel making good CPUs, which sounds pretty solid, because you also use those CPUs to facilitate all the other things in the transaction. And you obviously trust your bank because you are just sending your money from there. So what is this FGX Insight? It is basically a runtime. You can write programs further in C or in Rust, but it uses a specific C runtime, so it's not that easy. Because not all libraries are available. Sometimes you need to write your own, even if it's a simple library. And another problem is that this runs directly on the CPU, so it needs a special cloud hardware. It can be just any Docker VM, like everything else. It costs a bit more because it needs to use a physical machine. But services like this already exist and already are used, even by some of our partners right now. And what we needed to do is basically write a program that does all the steps I mentioned before, get the confirmation, sign it, send it to the blockchain, and that's it. But this is only the enclave part. Next, we have the contract that receives the confirmation. And this is where it was more difficult because of the implementation details of both the enclave and the Ethereum blockchain. Ethereum blockchain uses elliptic cryptography, and all the other cryptography uses RSA cryptography. So there are no primitives to validate the RSA signature by Intel on chain. So basically, you need to write RSA validation by hand, which is 500 lines of solidity, which wouldn't be a problem, but it also is costly to execute. So I think at the time we were writing this, it was costing like $1 to $3 to verify the RSA signature. But it worked, and it was like the DeFi dream. You can have completely trustless road from fiat to crypto without any trusted party, just a quiet middleman with an Intel stamp of approval. You might ask, what happens next? What happened with this product? Basically, it was very nice, but it was not very useful for people. Turns out people just want to buy crypto and sell crypto, and they don't care. They want it to be fast and easy. So following this liquidity pool model, we also added credit card payments, and because credit cards can be charged back, and they are not final like bank transfers. It's also really complicated to use an escrow because then if you do a chargeback, there are many problems next. So we had an option to sell crypto directly from our liquidity pools. This was like not a trustless transaction. And this is the model that prevailed. What proved best for us was the ease of use and speed for the users. Users want to enter a crypto application and buy crypto, and that's it. No additional steps, no waiting. They don't need the confirmations. And they trust us enough to just send it. Yeah, but all the stuff that I mentioned is still available. If you want to read the contract I mentioned, it has verified source code on Etherscan. It's not a fake link. It's the contract that actually was throwing money around 6 years ago. There is a nice article our dear friend Piotr wrote when we were working on the SGX oracles. And that's me. Yes, it's a typo. It was a test. Do you have any questions? Because I know a lot of the systems. Maybe I can answer some.
Yeah, thank you for your presentation. It was very interesting. I'm Alexander Kwaskov, FinTech Association, and my question about SGX. What about alternative from AMD or something like that? Do you have researched it?
By the time we were doing this was 2019, and there was no other solution. I think AMD did produce a trusted execution environment, but I don't know the name. I think Apple also has that, but it's not exposed for public use. It's used internally by the system. Yeah. Do you remember the name of the AMD stuff? Yeah. Okay, SEV. Yeah. Any other questions? We always add 10 seconds of grave silence. Yeah. All right. If you have any questions, you can still find me around later, and I will pass it on to the next speaker. Thank you.
Move blisko. 1, 2, 3. All right. Hello, everyone. How is everyone doing tonight? All right. Good. Yeah. So without further ado, do we want to take a 2-minute breaks? I see a little. No. All right. It's their loss then, if they're not here. Yeah. So thank you very much for coming. There's so many of you, so many of you tonight. And yeah, thank you. I don't know where Łukasz is, but thank you for the warm welcome, and thank you for Ramp for hosting this. And tonight, I would like to show you a little bit of what we're doing, a little bit of what we're working on at vLayer. But it ain't gonna be just showing off all the cool stuff that we're building. We're also gonna introduce some new ideas. I see some faces here in the audience that already been on my presentation, so that ain't gonna be new ideas for you, but some new ideas that you might or might not have already stumbled upon, or if you did stumble upon, that might be some ideas that you didn't have a chance yet to fully understand. So hopefully it's gonna be helpful for you. So we'd like to think we're building like Solidity 2.0 because we're bringing just so much new and cool features to Solidity that you can think it's like a major upgrade in Solidity language itself. And the 4 features that we're bringing, we call time travel, teleport, web proofs, and email proofs. And I'm going to walk you through each of them. But first, let me explain you how the new execution model that we introduced works. How many people already are familiar with zero knowledge stuff? Right, this is roughly 30% of the audience. So I know this guy knows about zero knowledge, but he didn't raise his hand. So it's 30% plus 1. So anyhow, we introduced this idea that is, for anyone that is already familiar with zero knowledge, gonna look very familiar. So we introduced the new type of smart contracts, 2 new types of smart contracts. One we call prover, one we call verifier. Both smart contracts are standard Solidity smart contracts. And the prover, which in our case inherits from the prover contract, which is just a base class, is executed off-chain. So this part of Solidity code is executed off-chain, not on-chain, not on layer 1, not on layer 2, but just on any computer or in the cloud. And the important difference between normal smart contracts and the prover smart contracts or other type of smart contracts is everything you pass is private. In a sense, it ain't gonna be ever published on the blockchain. And the smart contract has all those superpowers I talked about before, and I'm gonna talk much more about. To show you a little bit of the code, I know that a lot of you here are technical. I know there are some non-technical people here, so I'm gonna have more technical slides and also a lot of very non-technical slides to make sure everybody gets interesting content tonight. So this is a prover smart contracts. We're gonna prove that someone owns Bored Ape NFT, and we're gonna just say, okay, at this specific chain, at this specific block, we require that the owner of this specific ape is the owner, right? Okay, so we pass 2 arguments, owner and the ape ID. The ape ID is actually a private argument. So we're just gonna prove that the person has some ape. We won't tell on-chain which specific ape. And we're gonna return to 2 variables. One is the owner address, and one is the proof, which is the magic of the ZK, which I'm gonna explain what it does exactly in the next contract, which we call verifier. The verifier contract is even more like any other smart contract on chain. It inherits from the verifier, just a base class, and it can verify whatever prover did using the only verified modifier. And this is executed on chain, on layer 1, layer 2, whatever you want, wherever you want it to be. So here is an example. So here is an airdrop contract. Let's say we want to do airdrop for any person that owns an Bored Ape NFT. So we pass 2 arguments. The first is the proof, and the second is the owner. So these arguments that we pass are exactly the same arguments that we returned here. So just the same arguments. If we pass different arguments, the verification gonna pass. And we use this only verified modifier. Everybody remembers what the modifier is? Every technical person remembers what the modifier is? Okay, 0 hand. Oh, there is one guy at back. So for that guy, this modifier allows you to say, okay, whatever you pass here, it needed before to be returned from the prover function, right? So this is the address of the contract, and this is the name of the function, right? So we actually deploy prover on-chain, but we don't execute it on-chain just for a single source of truth, right? So that later we can refer to the prover from the verifier just right here, right? So this is the address of the prover contract, this is the name of the function, and we have this idea of selectors in Solidity, which makes it very long to pass the name of the functions. All right, and let's say we have verified that this person owns an ape, so we can transfer him some tokens. This is the whole airdrop. Obviously, in the real production code, we would also make sure that he cannot claim the airdrop several times. I skipped those in the sake of simplicity. Now we already get a little bit sense of the time travel in the first example. So time travel allows you to interact with chain with various historical blocks. So you can just call set block, and the prover jumps to a block at a certain point of time. So here it is. So for example, let's say we want to prove that someone is holding a specific token for a specific amount of time. So we can just set block to a millionth block and then check what the balance is. And then we can set the block to 1,100,000, check what the balance is, and we can return the minimum, and we say he was holding this amount of money for this specific period of time. So this is, by the way, if you're not impressed, you didn't code Solidity. Like, Solidity is extremely limited language, and it's just so hard when you want to do simple things like say, what was the average balance of the account in the last, month, week, whatever. Like, that's extremely difficult to calculate in Solidity. Now here you can do it in a relatively simple manner. Yeah, and here is a more advanced example calculating the average balance I was just talking about a moment ago. So you can see this is like production code that would compile. So it's a little bit more complex, but still pretty simple. A very similar feature to time travel is teleport. And teleport allows you to interact with multiple chains from in a single call. And you can use it in a very similar way, like you can do it with set block, you can do set chain, and the following function will execute in the context on the specific historical block on a specific chain. So let's say I want to jump to optimism to a specific block. I can get your balance. I can now jump to base on a specific block. I can get a balance, and I can return the total, the summary of the both. So that way, I can very easily create a primitive that says, oh, what is the cross-chain balance? What is the balance of this person across a few different chains? Yeah. So this is a pseudocode. This is actual production code. You see, that's pretty simple. And you can see all the different things like returning a proof. Now we're returning owner and a balance and all that stuff going to here. So that was two features that you might have that might have impressed you if you ever coded in Solidity and you try to do those cross-chain things or you try to do those historical things. But what if you could access web pages from Solidity? Wouldn't that be cool? This guy says it would be cool. All right. So yeah, that was what I was thinking when I was watching the last presentation. You could totally build ramp tonight with this stuff. Okay, so let me give you an example. So it was very technical before. We're gonna go very non-technical now. Before we got more technical again. So imagine. So I think, yeah. So before we go to building asset, that's 2 slides further, we're gonna build some real-world assets. So one problem with all those stable coins and all those real-world assets like stable coins to gold or US Treasury or whatever else is like we have so many of those tokens, and how do we know that this token that is being issued on-chain have actually there is actually a real-life asset backing it in the real life, right? And it's getting more regulated. It's getting less wild than it was a few years ago. But still, the reality of today is we have a few very big tokens like USDC that everybody trusts. But if you want to issue a new token, a little bit more exotic, how do I trust that guy that is issuing this token, right? So let's imagine we want to issue a token. Let's call it Quackles. So with web proofs, what you could do is, as the owner, as the issuer of the token, you could create an interface where you log into your bank, and you get the data from the bank that says, let's say there is a $2 million on the account, and you can prove on chain that you have $2 million, right? And only that you can issue a token, right? So you have 0 tokens, you want to issue $2 million tokens. You could only do that if there is a proof that money exists in the bank, right? So there is a little bit of nuance to what happens here. You can see there is a small icon on the top, and here, think on the side, this is an extension. This is a browser extension that allows you to go into a website, navigate to the right subpage, get the information that you're interested in, and generate a proof that you can later use on-chain. So that is one usage. I'm pretty sure there was something else important on the slide I wanted to talk about. Yeah, just want to mention that it can be an extension, could be also a mobile app. So we now have an extension, and the mobile app is coming as well. Right, so another example. So imagine you want to build kind of like an on-ramping business. If I could only come up with the idea what kind of company it could be. Let's call it OnRamp XYZ. So imagine there is a person there. There is a liquidity already on-chain, and there is a person who would like to use $200 to swap it for 200 USDC, right? So what he would be asked to do is to transfer money to a specific account. That could be actually directly to the person providing liquidity or whatever other account. And he clicks swap, he goes to his bank, he's doing a transaction, and when the transaction is done, he's generated proof that transaction was indeed sent. And when the transaction is confirmed, he can claim his 200 USDC. Does that make sense? Is that easy? All right, there's nobody at ramp here being angry or anything? All right, good. So let me give you a very simple example how web proofs could be used on in smart contracts. So this is get Twitter handle. So this is just a smart contract. We're gonna now mint NFTs, and you can mint an NFT with the name of your Twitter handle. So we can prove on chain, hey, I own this account that maybe have 2 million followers, or at least whatever number of followers, right? So with vLayer, the very simple way you could do that is you could just pass the web proof that was generated by the extension to the execution of the prover, and then the web proof already have functions like verify, which can verify this content of this specific website is coming from that specific URL with all those little details, and I can query that with my JSON Solidity JSON parser. Yep. Yeah. Yeah. So this is a pseudocode. This is actual production code. Like Solidity is full of those little modifiers, public, view, memory, so it makes it a little bit longer. But yeah, this is not very complex at all. Yeah, so web proofs allows to do cryptographic attestation of private data served by HTTP server. There is a JSON precompile and a web browser extension. As I mentioned, mobile application is coming soon as well. Good. And this is how it looks in real life. We actually were able to shorten the amount of steps here. But yeah, you just open the credential. You just go to the You hit a button in the application, it opens the website, it opens the extension, and the extension gets you there step by step. Through all the different stages, transfer the money, and when it's done, generate the proof, and then the proof is being generated. Good. Yep.
Exactly read is like the HTTPS request made by the browser and the responses, and why the and how does the JSON work?
Yeah. So there was a quick short question, but it touches a lot of topics. So I'll start from the end. So the last question I heard was, how is JSON being parsed? So this is happening in the prover. The prover runs full ZK EVM execution, and the EVM has a precompile for parsing JSON.
Yeah, so does it mean that the input is JSON?
Yeah, that means the input is JSON, exactly. So I think at this point of time, it's practical to parse JSON. You could parse more HTML as well. You can parse more HTML as well. It's not available on the ZK EVM yet, though. And so that was the second question, and the first question was, what is extension doing exactly? So it is a little bit complex. I have a separate presentation I could do on that, and I actually gonna at the end slides I'm gonna have some links to places where you can read exactly what's going on. So I ain't gonna go into too much detail. But what's happening here is this web proofs algorithm, they modify or they join TLS connection. So TLS, for probably most of you heard about it at least once, is an encryption layer on top of TCP/IP that is basically used by almost every connection in the world today. So HTTPS stands for HTTP plus TLS, right? So, and what these web proofs are doing is they introduce a new role between client and server. There is a new role called, different people call it different way, but I call it notary. And the notary is able to be included in the connection without ever seeing the unencrypted transcript. So the notary cannot see, okay, this is your private data, I'm looking at your private data. This is cryptographically impossible in this protocol, but it gathers enough information that when the connection is done, the user can send him a subset of the transcript, like for example, only $2 million, or maybe just the whole connection, but maybe without your session key that you don't probably want to share. And it gathers enough information that you can prove cryptographically that that came from this specific connection. Does that make sense?
Yeah, I was more interested about the other, but we can.
All right, let's leave it for the end then. I'm happy to answer all the questions. Just want to make sure I don't bore other people to death in the meantime, because I love getting into all the technical little details. So, all right, wallet email recovery. So time travel and teleport were kind of similar features, and web proofs and email proofs are kind of similar feature. What if I could get emails and use emails inside my Solidity smart contract? Would that be cool? Would that be cool? He says yes. All right. So wallet email recovery. So imagine you lost access to your wallet. Wouldn't it be cool if you can just hit like remind my password kind of flow, where you just kind of rescue my wallet kind of flow? And here is an example how it could work with a, and I think actually someone already implemented it. I think I read the news yesterday or 2 days ago that there is one wallet already. I'm not sure if it's that one though. Someone went to production recently. So there's been a little bit of experimentation over the last year or two, but someone went to production like yesterday or 2 days ago. So that's exciting times. So recover wallet. So you go to this, let's say I lost my key, whatever. I can put address of my wallet, and let's say, oh, this is a new address This is ENS address, could be normal Ethereum address. This is a new address I would like to have control over my wallet here. It sends you a email reply with a single word yes to this email if you would like to recover this and this thing, right? You hit reply, and it goes to the server, and the server can generate a proof that there was indeed an email sent from that specific address to, yeah, I made this presentation before Elon was controversial, so apologies. So, well, when he was less controversial. So, and the email server can generate a proof, and the proof can be, then taken on-chain. A similar thing, and we actually have a customer doing that, is there is, for example, in US, there is a law that says if you have a custodian, right? So custodian is someone who holds your funds. There is very complex law in US that says, okay, if you're an exchange, then you cannot do like all the things. There needs to be a custodian, there needs to be a transfer agent, there needs to be a party responsible for swapping and all that stuff. So it's very well regulated that like money in general is not laying around in random places. There are special companies called custodians, and they are obligated to send you an update about state of your treasury or a state of your custody. And you know, like they use very modern protocols like email oftentimes to do that. So you could very well use the same real-world asset example we used before, but instead of logging into a bank, just parse an email. And we actually have a customer in this stablecoin space. He's doing a gold stable coin that is pegged with gold. That is doing exactly that. All right. Again, go a little down to the code. So this is a get wallet address. We pass unverified email. We can verify the email, and we can, ask him about all kind of things like, hey, is the title, is the subject of the email of this specific format? So there is a whole regular expression precompiled that allows you to query email. And here is a real life example how it would work. So in this case, we're doing a simple example here where you can mint an NFT proving that you work for a specific company like Microsoft or Google by just sending an email that gets proven on chain. And again, the interesting property of that is that we're passing the whole email, but we're returning only the domain, or we should at least be, returning the whole address, but there's nothing that stops from just returning, so I can prove I work for, Microsoft, Google, or whatever else company. Yeah, so I already talked about cryptographic proving, about regular expressions. If you want to start using it, just download the vLayer app, We have a bunch of examples, all those examples that was about minting NFT from email, web, and so on. We have working examples that you can download and start playing with. We also have a pretty good explanation, a whole book explaining how the whole system works. And yeah, for those of you who did actually touch on zero knowledge proofs, I want to talk about all the things I want to talk about. So if anyone tried to do those emails before, or web stuff before, or like storage proofs that allows you to historical approach to data, that those might be the things you have to learn about. So first, there's a little bit of math, and you need to write circuits which require fields, and knowing what the curves are and secrets are. Oftentimes, you need to use exotic languages like, like Circom or WAR. If you want to do emails, you need to know what the KM records are. If you want to do storage, if you want to do time travel or teller functionalities, you need to know about storage proofs, Malcolm mountain ranges, and so on. Even the best thing you can get, there is now something wrong. Still need to know what the headers are, what slots are, what ABI encodings are. So this is all the Ethereum under the hoods that you don't need to know about. You don't need to draw advanced architecture diagrams. Yeah, this is the whole execution model that you need to understand. All right, and we actually went into testnet 3 weeks ago, so yeah, feel free to try out. And so we actually wrote 3 reports that goes in detail about all those different things, what the web proofs are, what are the security properties of that, about emails and on-chain proofs. as well. So this is business language. This is not something that need to kind of understand solidity or anything like that. For those who do like mathematics, quite a few